Hello and welcome to the first part of our unit on wave optics. In this part, we're going to focus on diffraction. And to begin with, what we're going to discuss is what do we mean by wave optics? Well, photons or light, like many other phenomena in physics, can be viewed as either waves or as particles. With light, I have to decide how I'm going to view what's going on in order to be able to explain what's going on. In order to understand diffraction and interference effects, what's going on in this unit, we need to consider light as a wave. But if I want to look at like photoelectric effect, for example, in that case, for that experiment, I would need to consider light as a discrete package of energy, or in other words, a photon. So what is diffraction? Diffraction is the bending of light as it goes around an obstacle. Diffraction is why you can hear sound down the hall and in another room from your, the radio of the person at the other end of the house. Diffraction. For this, we are going to consider single slit. So here I have a barrier with a hole in it. The dotted line is just for reference and goes from the barrier just perpendicular down the center. And for this, what I'm going to do is I'm going to consider waves coming in that are plane waves. So they have very nice parallel wave fronts. If you want to think about this as a wave, every time you see a line, think about it as being the crest. So I'm going to try to draw a trough in between to give you the idea. Okay, so these waves hit this slit barrier, like a window, if you will, and when they go through, they're no longer straight, they bend. Okay. Now, the peculiar thing that happens is you get this bending, and then you're going to get a region where it kind of fuzzes out, and then you're going to get a region over here where it gets dark again, or not dark, bright again. And that results in a light pattern that looks like this. So again, I put my plane waves in, they bend, and on the far side I get this region of, or this series of bright and dark spots. Now, I'm going to define an angle, and that angle is going to go from the center of the slit to the dark spots. So I'm going to try to get the first three done. I could technically go to either side. This angle I'm going to call phi, and I'm going to number these dark spots as n equals 1, n equals 2, and n equals 3. I could go to the other side as well. This would also be an n equals 1. This one would be an n equals 2, n equals 3. I'm also going to define the distance from the slits to the screen as L, and the width of our opening here as S, and the distance from this dotted line to where the dark spot hits as B. So the way that you can tell where the dark spots are is that S, the slit width, times the sine of the angle has to equal n, which is the number you're looking at, times the wavelength of the light. Measuring that angle is difficult, but if you look, we have a triangle where L is on this side, B is on that side, phi is here. Sine phi is technically the opposite side B over the hypotenuse, which would be this side, because here's our 90-degree angle. But if phi is small. If we're dealing with a small angle, which we can make happen, then h and L are going to be about the same. So I'm going to define this as B over L. So with that, I can write that this is going to be approximately SB over L. Okay. If you're looking at the equation sheet, this is currently number 47. So now let's look at a simulation which will help us to look at the behavior of single slit diffraction. So here is the simulation. I'm looking at this one, single slit diffraction and double slit interference. So right now there are three things that I can change with sliders. I can also change color, and I can change the type of opening. Right now I want to be on single slit. Because I'm on a single slit, the distance between the slits doesn't make any effect. There isn't a distance between the slits because there's only one. However, if I change the slit width and make it bigger versus smaller, I do see effect, with the smaller width giving a broader peak. So it makes the whole pattern overall wider. I can change the distance to the screen, and as I make the screen farther away, it also makes the pattern wider. It gives it more time to spread out as it leaves the slits, if you want to think about that. If I change the color from red to green to violet, we see that the red pattern, the one with the biggest wavelength, has the broadest peak again, the broadest pattern. And that is consistent with the formula that we just wrote down. One last thing, let's work a simulation, or let's work an example, dreadfully sorry. So we have monochromatic light of wavelength 653 nanometers, so lambda is 653 nanometers. We're told the angle between the first dark fringes on either side of the central maxima is 3.2 degrees. Now back up a second. Notice in the formula I defined phi as relative to the central axis. What this problem is giving us is not that angle, but this full angle. So that tells me that 2 times the angle phi is 3.2 degrees, which means that phi equals 1.6 degrees. And I want to know what is the slit width. So what is S? So for part A, S sine phi equals n lambda. I want to know S, so I'm going to solve for it. S equals n lambda divided by the sine of the angle. N in this case is 1 because I'm told it's the first dark fringes. So 1 times 653, I can work in nanometers, so I'm going to leave that there, times the sine of 1.6 degrees. So 653 divided by the sine of 1.6 is 2.33 times 10 to the 4th nanometers. And I could do a unit conversion to get that into microns. That would be 23.3 microns, which is not unreasonable. For part B, it says if the screen is 2 meters away, so it's giving us L, how wide is the central peak? So this part is asking for what is B, and it wants to know the width of the entire peak. And again, if you look at our definition, B goes from the central line to one side, so we would need to multiply our result by 2 in the end. For that, I need that n lambda equals SB over L. I can solve for B is going to equal n lambda L divided by S. So that's 1 times 653 nanometers times L, which I told was 2 meters, divided by S, which is 2.33 times 10 to the 4th nanometers. Now I got to watch my units a little bit here because I have nanometers, nanometers, and meters. The nanometers cancel. My units in the end will be meters, which is okay. So 653 times 2 divided by 2.33 times 10 to the 4th gives B equals 5.6 times 10 to the minus 2 meters. And again, I need to multiply that by 2. So the answer to part B is that 2B is 1.12 times 10 to the minus 1 meters, which is a very broad pattern. And that concludes this part. In the next part, we are going to look at two-slit interference.